Hello everyone, welcome to our class. Let's continuously study Chapter 4, Convertibility of Energy, Exergy Analysis. The third section, Calculation of the Exergy. Here, let's have a review about environment and dead state. We know any system is always in an environment. Any exergy must be relationship with an reference environment. When a system is in an environment state with P0, T0, V0, we say the system is at the dead state. In this case, the system there cannot be changed action between system and environment. No action, interaction. Therefore, no potential for developing work. Generally, environment is regarded to be compressible system. Is with large uniform in P0, T0, the mass is very large. Capacity is very large. Heat capacity is very large. So in the environment with T0, P0, it is a very big system. So most cases cannot be changed. Exergy calculation. How to calculate the exergy? Firstly, the exergy of work. Work can be separated into two kinds. Firstly is available work. Another kind is unavailable work. Two kinds. So, practically system, the work equals W useful plus W unuseful. Two parts together is the practical work. Also, maximum available work is called exergy. If the system volume not be changed or the network exchanging with surroundings to be zero, no work exchanging with the surroundings, then all of the work over the boundary is exergy. Therefore, the useful work just is the exergy. Noticeable in expansion work, in expansion process, the work used to push surroundings is not useful. For example, here is a cylinder. When the piston moves, certainly the piston push some surroundings. So do some work P0 V2 minus V1. Push the surroundings. Do the work P0 times V2 minus V1. This part of the work no useful. So it is not exergy. If P0 is the pressure of the surroundings, V1 and the V2 is the volume before and after system change. So the P0 times V2 minus V1 is push the surroundings the work. We think this part of the work no useful. Therefore, the exergy of work must minus this part. So exergy W is equals W minus P0 times V2 minus V1. We can do some calculation, but the integration is M from 1 to 2 integration P dV minus M integration from 1 to 2 P0 dV. Finally is M from 1 to 2 integration P minus P0 dV. Here, only this part is the exergy. It is the exergy of work. Another question is exergy of heat. We know the maximum theoretical work obtainable from heat energy is just the exergy of heat. When the temperature Th of heat source is higher than environment T0, the heat Q can be changed into maximum work by Carnot's cycle, Carnot engine, which is the exergy of heat Q. So we can use the Carnot ratio to calculate the exergy of heat. EXQ equals 1 minus T0 over Th times Q. 1 minus T0 over Th just is the Carnot ratio. T0 is the temperature of environment. Energy of heat. Certainly, the exergy of heat only part of the heat. Another part is energy. Always sum of heat cannot be changed into work. This part is energy. So energy is Q minus EXQ. EXQ is the exergy. So it is T0 over Th times Q. So this part of the heat is energy. Okay, another question is the exergy of cooling power. What's the cooling power? The heat energy which the temperature Tc is lower than the environment temperature T0. T0 larger than Tc. In this case, the heat energy is called as the cooling power. So cooling power is still thermal energy, but its temperature is lower than environment temperature. In this case, how to calculate the exergy of the cooling power? For example, in this system, the high temperature reservoir is the environment temperature T0. The low temperature reservoir is Tc. We obtained some energy Qc from the cold reservoir Tc. This part of energy is called cooling power. So Qc is cooling power. We can use some work outside the work to drive the heat pump. So draw the Qc into environment. So this system, we can think it is a very special refrigerator, but in this case we need is Qc. So Qc, how to calculate the exergy of Qc? We can think another way. Let some refrigerator to drive the cooling power Qc to move to environment. Some work has to be paid by surroundings. In this way, the cool source gives out the heat energy Qc, and environment obtains heat energy Qc and W. W is outside to give the work. Finally, we get the cooling power Qc. So this Qc certainly includes some exergy. So we can calculate detail by this picture, discussed by this picture, to make the cooling energy Qc with temperature Tc in the environment with T0. In this case, the theoretical maximum work we have to pay is exergy of cooling power. In this case, we have to pay some work to the system. We can draw the thermal energy Qc, let's send to the environment. In this way, we can use the reversible Carnot refrigerator to do this work. So this work is smaller, is lowest. As long as we calculate the work W used to drive the refrigerator, then the exergy of cooling power will be obtained. So in this case, we can calculate the cooling power exergy. It is a little difficult. It's a little difficult to understand. Similarly, we can assume that a reversible engine works between two heat sources with T0 and Tc respectively. The engine gets the heat Q from the environment T0 and sends the heat energy Qc to the cooling source Tc. At the same time, the engine do the work W for us. So in this case, W is 1 minus Tc over T0 times Q. But we should calculate the exergy of cooling power is not Q the exergy. So we can do some change. Based on the Carnot principle, the efficiency of engine is it equals 1 minus Qc over Q equals 1 minus Tc over T0. Because the engine is reversible, no entropy generation. So Qc over Tc minus Q over T0 certainly is 0. From here, we can calculate Q equals T0 over Tc times Qc. Finally, we can calculate the W is Qc times T0 over Tc minus 1. This W just is the exergy of cooling power. Cooling power exergy. Please remember, T0 is larger than Tc. So T0 over Tc minus 1 is positive. That's to say the exergy of cooling power Qc in environment temperature T0 always is positive. Here is the exergy of cooling power. Noticeable, all exergy is positive, no matter how coming from work, heat, and cooling power. Any energy, the exergy is positive. The evaluation of exergy utilization. Originally, we only noticed the share of exergy which is utilized in quantity, but now the share of energy utilized in quality also is noticed. No matter how the quality, but the quantity. So thermodynamic perfect degree and exergy efficiency is often used as the standard to evaluate the energy utilized. Just how to evaluate the utilized. We give some very special the concept, the thermodynamic perfect degree. For producing work device, the perfect degree is defined it R equals W export actual. This part of work is in actual process. The system gives the work over W maximum reversible. W maximum reversible is in the reversible process, the system do the work. So it R always is smaller than 100%, always smaller. The picture like this. The high temperature TH, low temperature is TL. If some reversible engine working between the temperature reservoirs do the work WRE certainly is larger. In the actual system, some irreversible engine working between these different temperature reservoirs do the work W certainly is smaller. So there is some work waste. For producing work device, so the ETR is W export actual over W maximum reversible. This efficiency, we can call it perfect degree. For waste work device, waste work in the reversible process certainly is waste work is smaller. In actual process, irreversible process, certainly waste work more. So in this case, W import sent into the system. RE is the divide. W import actual is in irreversible process sent into the work is larger. So ETR is still more than 100%. The thermodynamic perfect degree must be smaller than 100%. Another concept is Exergy efficiency. Exergy efficiency is defined as Exergy equals EX used over EX cost. EX used means the Exergy be used. EX cost means the Exergy by sent into, but outside give the system. So Exergy balance in the process generally is input the Exergy minus export Exergy minus Exergy destruction, because Exergy is not conversation. There is some Exergy destruction equals the Exergy change. So it's not the same as the energy balance equation, because in this equation includes some Exergy destruction. Thank you.